Good evening, everyone. Let us continue with our discussion. So, last class we started discussing about columns. So, let us study the course contents for this week's class, which was basically we will be continuing with the study on the design of columns. Okay, so let us start. So, as we all know, uh, beam slabs, columns, footing, all those. Okay, so these are designed based on various taking into account various types of limit states, okay, like flexure, shear, axial loads, and like various torsion moments, etc. Okay, so basically in beams we mainly design for flexure and shear, as you remembered, as you may have remembered in the initial classes. Then we came to slabs in the last few classes, where we basically designed the slabs for flexure. Okay, so we only design for flexure because the depth of slab is very less. Okay, so that's why we did not take into account for the shear component. In case of columns, basically we go for axial force as well as moment. Axial force is basically the compressive load. Okay, and moment is the the if the load is not acting at the center of the section, so there will be some moment generated, right? So that moment we have to take into account, right? And that may result in flexure also. Okay, so that's why we mainly talk about axial force, that is compression force, and moment. In case of footing, we mainly design for the case of please mute everyone so that it is easy for everyone. Yeah, thank you. So in case of footing, we mainly design for axial force and moment. So in this case, in the case of footing, the moment is maybe mainly torsion or even flexure, and apart from that there may be shear also. Okay, so I have incorrectly given these arrows, so I'm sorry for that. So many various forces can act. Okay, and similarly there may be some components in the case of staircases also, so we will be going through that also in some later classes. So yeah, so this class is mainly dedicated for columns. So let us start. So as you can see, so these were the type of designs we had carried drawn designed these were the designs we had calculated. Okay, for the case of beams and slabs, that is monolithic beams and slabs that were cast. So yeah, so that was mainly for beams and slabs, which we have been doing from the initial classes. So in case of columns, if we start, so basically columns are of various shapes. Okay, various shapes of sections are there. Some columns may be rectangular in size, some may be circular, some may be square, okay, in shape. And so what are the parameters? Okay, so what are the parameters we have to take into account? One is a dimension, which can be rectangular, circular, square. Second is the minimum number of bars, that is a reinforcement, or we call the longitudinal bars, basically the main reinforcements, right? So that we have to take into account which type of like what are the bars we have to like as per design, how many bars we need to provide, and that should be greater than the minimum number, right? Thirdly, we have to we have to find like that can be calculated based on the minimum reinforcement. Okay, so minimum area of steel that is required. Similarly, minimum bar diameter, okay, both for main and transverse. So there must be limit for that also, based on the based on the IS code and the amount of area we transverse steel area we would require, right? And also there will be spacing of bars. Okay, so that also will have some special conditions for calculation. And sixth is the transverse reinforcement. Okay, so that is the secondary reinforcement. In case of beams we call that stirrups, and in case of column we call that tie bar. Okay, so basically it is the same. So in case of beams it is called stirrups, in case of columns it is called tie bars. Okay, and that is mainly provided to resist the shear. Okay, so resist the shear and provide adequate shear strength. Okay, horizontal transverse strength for the reinforcement bars. So as you can see, these are the examples of tie bars, and these are the main reinforcement bars. Okay, so the this spiral circular the yeah the this pentagonal shaped this one bars are called the tie bars, and the vertical bars are the basically the main reinforcement or longitudinal bars, right? So here it is in helical shape, the tie bars, or circular shape. Here it is mostly in pentagon shape, right? So various types will be there based on the reinforcement provided and the design, right? So apart from that, columns can further be classified into various types such as short column, long or slender column. Okay, so we need to define what are the various types of columns. Again, there is a special column which is called a pedestal. Okay, so pedestal is basically a column in which the effective length is always greater than three times the I think it should be less. Okay, less, it should not be greater than three times the least lateral dimension. Okay, so this is the clause. So I'm sorry for this mistake. So basically if this is a basically a very short length column where it should not be greater than three times the least lateral dimension, so it should be not greater than. Okay, so this is as per clause 25.1.1 page 41 IS 456 2000, right? So yeah, so as I told you, what is a short column? So short column is basically a column where the L by D value, okay, from both the axes should be less than 12. So if it is less than 12, so it is basically called the short column. Similarly, the slender long column is basically a column which is having the L by D or B ratio greater than 12. So actually these slender columns, if you go more into more detail, so they are again classified into this one medium columns and long columns, right? So medium columns will have values in between, I think 12 to 120 or something like that, and long columns are having the L by B or D ratio more than that. Okay, so it is not just greater than 12, it is about greater than 120 or 150, something like that. But that is we don't need that much in detail. So basically we just need to have an idea what is a short column. So that is basically the condition is the L by D or L by B value should be less than 12. Okay, and for finding the effective length, okay, so there are various cases. Okay, so that effective length is required for the calculation. Okay, so for finding that effective length, so there are various cases. There are 7 cases that we have to follow as per the annexure E of table 28 page 94. Okay, so yeah, so if you go to that table, there are 7 cases. So what are the cases? So first case is when the column is effectively held in position and restrained against rotation in both hands. So basically when the columns are fixed. Okay, so that is the basically the case where for the normal columns, right? So they are effectively held in position as well as restrained against rotation. That is basically both hands are fixed. So in that case, the effective length is taken as the theoretical value for effective length is taken as 0.5 times, that is half of the L, which is the unsupported length. Okay, so unsupported length is basically the clear distance between the N restraints. Okay, so we generally take the half of the N unsupported length, so that is the theoretical value, and recommended value is basically 0.65 L. Okay, so that is when the both ends are fixed. Similarly, when effectively held in position at both ends, restrained against rotation at one end. So that means the one end is fixed, but other end is pin supported. Okay, pin or rolling support. Sorry, not rolling supported. Basically pin or support, hinge supported. Okay, so that is one end is fixed. That is it can move or rotate, but the other end can rotate, but it is not. It can rotate but fixed. Okay, it can rotate, but it can translate. Okay, so that is one end is hinged and other end is fixed. Okay, so if in that case the theoretical value is taken as 0.7 L and recommended value is 0.8 L. Okay, so L, as I told you, is the unsupported length or the clear distance between the N restraints. Okay, third case is effectively held in position at both ends but not restrained against rotation. So that is basically the pin support or the hinge support. Okay, as I like this, as I told you. So if the both ends are hinge supported or pin supported, in that case the effective length is equal to the unsupported length. Okay, so in both, for both the theoretical and recommended value cases, so the same value will be taken such as the unsupported length for the case of effective length. Okay, fourth condition will be effectively held in position and restrained against rotation at one end, that is one end is fixed, and other end restrained against rotation but held in position. Okay, but not held in position, sorry. So if one end is fixed, okay, but the other end can move but cannot rotate. Okay, so in that case the theoretical value is again 1L, that is same as unsupported length, but the recommended value is more like to take 20% more than the unsupported length, that is 1.2L. Okay, Similarly, in the fifth case, effectively held in position and restrained against rotation in one end, that is fixed in one end, and the other end partially restrained against rotation, but not held in position. Okay, so that means this can again this one end is fixed, but other end can move but cannot rotate fully. Okay, so partially it can rotate. Okay, so in that case also the theoretical value is not given, but recommended value is taken 50% more than the unsupported length, that is 1.5 L, for finding the effective length. In the sixth case, it is effectively held in position at one end but not restrained against rotation. So this is pin support. Okay, one end is pin supported and the other end restrained against rotation, but not held in position. So other end can move but cannot rotate. So one end cannot move but rotate, but one end cannot move but rotate, and the other end can move but not rotate. Okay, so it is the opposite. Okay, so one end the movement is possible, this the movement is possible, here not possible, but here rotation not possible, here it is possible. So in that case the theoretical value will be of effective length will be twice that of the this one, uh, the unsupported length, but the and also the recommended value. Okay, so both the values, recommended and theoretical, for effective length will be twice the unsupported length. Okay, in the seventh case, so effectively held in position and restrained against rotation at one end, that is fixed at one end, but not held in position nor restrained against rotation at the other end. So the other end is basically free. Okay, so if one end is fixed and the other end is free, then again the theoretical value will be twice the that of unsupported length, and also the recommended value will also be the twice the value of the unsupported length. So both the theoretical and recommended value for effective lengths will be, yes, generally we take the theoretical values. Okay, so yeah, that can be done, or it will be mentioned in the question itself. Okay, so we can take both the cases, and in most of the cases it is the same. Okay, so we will be basically considered we will be basically working with the this one, pin supported values. Okay, either pin that is hinged at both ends, or we will be working with the this one, the fixed at one end and free at other end. So generally these are the cases which are given in questions. Okay, so if you see here also it is taken 1L in both the values, and here also you will see it is twice L. So the measure cases both the values are equal. Okay, so these are some exceptional cases. Okay, these are some exceptional cases, that's why this is mainly the recommended value is mainly it is taken to be uh, yeah. Yeah, so we generally take the theoretical value. If you see now, we will generally take the zero point 0.5 L, but we can also take the zero point 0.6 L. There is no hard and fast rule to take any, any specific case. Okay, so both cases are correct, but you just have to mention which values we are going to take. Okay, so you just write it in square, like write in beside the value you have taken. Okay, so if it is mentioned in the question, so you can take a specific value. If it is not mentioned, then you can take any value. I think that is, that will answer your question. Okay. Okay. Yeah. So in the case of like the seven case, if one end is fixed and the other is free, so the in the case of theoretical value, and both also in the case of recommended value, we will take the twice L, where L is the unsupported length. Okay. So yeah, so that is the seven cases which we will be considering for the design purpose. Okay, so yeah, so these are the pictures of the casting of columns. So before casting, we generally fix the caging of the reinforcements and then go for casting, right? So yeah, so basically for design of columns, we will be working with basically a few limit states, right? So one of the main limit state is the limit state of collapse in compression. Okay, because columns generally fall in compression. Okay, axial compression. So here one is compression and other is also flexure. Okay, because if the axial load is acting at some distance from the center of the cross section, so there will be definitely some moment component or the bending component, right? So that's why flexure also needs to be considered, and the limit state of flexure in the case of beams. Okay, so almost most of the things are almost similar, apart from few things which we will see in this in the coming slides. Okay, so let us see. So basically the assumptions, if you see, those are basically the same. Okay, so like the plane section normal to the axis remain plane after bending, so that is the assumption which we also took in the case of beams. Similarly, the maximum strain in concrete at the outermost compression fiber is taken as 0.0035. So that was also used in the case of beam when we tried to find the equation for strain and stresses, and equating the forces, right? And the tensile strength of the concrete is ignored, because we always assume that concrete is good in compression and bad in tension. Okay, so apart from that, the stress block may be assumed to be rectangle, trapezoid, parabolic, or any other shape which results in uh, prediction of strength in substantial agreement with the results of test. So based on the test which we may perform actually experimentally, so we may take the stress block as per how the behavior is seen. Okay, it may be rectangle, trapezoid, parabola, or any other shape if we have performed the experiments. Okay, so apart from that, the stresses in the reinforcement are derived from representative stress strain curve for the type of steel used. So basically we use the stress strain curves as we did it for the beam and slab design also. So based on this, we basically take the values. Okay, and for design purposes, the partial safety factor gamma m is equal to 1.15 for the reinforcement. So that is true for the limit state method, right? So it is a partial value of the actual value of factor of safety, which was around 1.8, which was used for working stress method. That's why it is called partial safety factor, right? And as we all know, the maximum strain in the tension reinforcement in the section at failure shall not be less than Fy by 1.15 ES plus 0.002, or 0.87 Fy by ES plus 0.002, right? So this is the maximum strain. It should be greater than the that value, that this limiting value. In the case of compression, it is 0.0035. In case of steel, it should be greater than Fy by 1.15 ES plus 0.002. So the maximum strain is basically a function of the yield strength, right, of the reinforcing bar. So yeah, so that is what it is taken said. And apart from that, there are a few extra cases also, like that has been mentioned in the IS code, IS 456. So specifically for limit set of collapse in compression, so the maximum compression strain in concrete in axial compression is taken as 0.002. So this is written in some clause in IS 456. Also, I think I forgot the clause, but it is mentioned in the IS code, so we have to refer that. Okay, and yeah, so this is a representative diagram, right? So this zero for the concrete basically. So as we all know, so it will be 0.002. So up till here it will be parabolic, and after that it is saturated. Okay, it flows constantly up till a strain of 0.0035 for concrete, and the strength is 0.45 fck. Like fck we divide by 2 times 1.5, we divide one for accounting for the uncertainty in design, and other for the material, right? So yeah, so basically the assumptions, yeah, so few assumptions which are different from the other case is that the that is the case which we design in beam. So one case which is different from that case is the maximum compressive strain at the highly compressed extreme fiber in concrete subjected to axial compression and bending, and when there is no tension on the section, shall be 0.0035 minus 0.75 times the strain at the least compressed fiber. So yeah, so generally the maximum compressive strain at the outermost fiber is 0.0035, right? So as you saw here, but in case of in case of concrete subjected to axial compression and bending both, and when there is no tension, then it will be little less. Okay, so there it will be, because both are acting, right? So there it will be 0.0035 minus 0.75 times the strain at the least compressed fiber. Okay, so in case of beam, if you remember, there was no concept of axial compression, only flexure or bending was there. But in case of columns, there are mainly these two factors, both flexure and axial compression. So in case of columns, because these two are there, so definitely the extreme fiber strain in concrete will definitely be lesser than 0.0035. And how much lesser? It will be 0.0035 minus 0.75 times the strain at the least compressed fiber. Okay, so yeah, so that we have to take into account, and that's why there can be these three cases in columns. One, it can be axially loaded, that is axial compression. Second, it can be uniaxial bending, so that is only one component of moment is acting, only one direction it is acting, one axis it is acting basically. And thirdly, it can be biaxial bending, that is both are acting together. Okay, so these are the three cases that can happen in a column. Okay, so yeah, so if you see like now let us go for the let us go for finding the equations and try to find the moment carrying capacity. Okay, so at a strain of 0.002 for a case of axially loaded columns, okay, so which is basically under axial compression, in the case of Fe415, okay, the load is basically taken as AC into 0.45 FCK. That is the the load capacity is basically the capacity of the concrete plus the capacity of steel, right? So in case of Fe415 at 0.002 strain, the capacity is the stress capacity is taken as 0.75 Fy. Okay, so that is a if you say that is like we are underestimating the capacity of the this one of the reinforcement bar for a better design, right? That is the concept of limit state design. Okay, to underestimate the capacity of the structure and overestimate the loading conditions. Okay, that's why we multiply loads by 1.5 and divide the material properties by the partial factor of safety. That is underestimating the quality of the material and overestimating the amount of load that will be acting, right? So for Fe415 we take 0.75 Fy, okay, at a strain of 0.002, the capacity of stress capacity. And for Fe250 we take it as a 0.87 Fy, which is normal, right, by dividing 1.15. Okay, so in case of the this one load carrying capacity, the total will be the load carrying capacity, total load carrying capacity of the column will be load carrying capacity of the concrete plus load carrying capacity of steel, right? So the load carrying capacity of concrete will be AC into 0.45 FCK, whereas the load carrying capacity of steel, it will be AS into 0.75 Fy minus 0.45 FCK. This is because only steel is not acting, right? So there is steel which is at a particular distance center to center between the inside the concrete. Okay, so we can say that in a way we can say that steel rebar is a mixture in concrete, right? So that's why the total stress, okay, so it will be taken by both the concrete and steel, right? So we need to subtract that the stress taken by the concrete, so that's why it is AS into 0.75 Fy minus 0.45 FCK. So that is the load carrying capacity, that is the design philosophy basically. Okay, so like this they calculate, and basically AC prime this value actually, so this is basically area, total area minus the area of steel. Okay, so that's how it is calculated. So we'll see it when we solve we'll see the examples. Okay, so that is the case. And similarly in the case of Fe250, the load carrying capacity will be AC into 0.45 FCK plus AS into 0.87 Fy minus 0.45 FCK. Okay, and when the point of load, okay, so when the point of load acting from the center is within 5% of lateral dimension, so if this is the center of the section and the load acting is somewhat it is within this within the 5% of the lateral dimension, so if this is say 100 mm, okay, 100 mm depth, okay, so this 5% is 5 mm, right? So the load acting will be 5 mm, within 5 mm from the center of the section. Okay, in that case the axial load capacity of the member or the carrying capacity on the member will be 0.9 times into 0.45 FCK AC plus 0.75 FIAS. So this is as per the IS code. Okay, so you have to follow the, like, they have found out some experimentally and given this empirical relation. So from IS code we find that axial load on the member when the load is acting from about 5% from the center, like the load acting is within 5% of lateral dimension from the center. In that case the capacity is 0.9 into 0.45 FCK AC plus 0.75 FY AS. Okay, so solving this we get P equal to 0.405 FCK AC plus 0.6750 FYAS. Okay, so this is an important formula. Okay, so this is as per clause 39.3 P71 IS 456 2000. So please write this equation in your like some notebook or some notes. Okay, so take this as note, because this some relevant questions related to this come in exams, entrance exams like it. Okay, so this formula we will be using in solving the problems, many problems, various problems. Yeah. Okay. Okay. Actually we should deduct it. Okay, because to get the, actually the reason behind not deducting is because as compared to the area of steel, the area of concrete is much more, right? So if you see what is the reduction factor, it will be less than 10%. So almost it is equivalent, right? So that's why they did not deduct. But actual, if you see the realistic case, it should be deducted. Okay, so then you will get the accurate value. Yeah. Yeah. So basically, like as per like my understanding, uh, we should always go for the factored load. Okay. So like if it is not given as factored load, or also like in some cases they consider both as the same. Okay, the design load and the factored load. Okay. So it is up to your conscience. Okay. But generally we should. Yeah. 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 Ideally that should be done. Ideally that should be done. Actually I am taking the notes from like the sir's course only, right? So because sir has mentioned not to explain something different from my subject matter, so that's why I am taking the same thing. So it will help you in understanding better. But for exams it is better to find always calculate the design, the factored load. Okay, so in that case it's better to multiply by 1.5. Okay, these are just some of the representative examples. So in this case, for example, they have not subtracted the AC minus AS, right? But it should actually be subtracted. Okay, this is basically AC prime. Okay, so but this is just for generally for your understanding, right? So that's why I will also suggest you to practice as much problems as possible. Okay, so that will help you clear your all the concepts and the criteria required for designing. Okay. Yeah, so I'll be covering the solve examples, right? So you can wait for a few minutes. After the completing of the slides, course slides, we will directly go to the solve examples. Okay. Okay, then we will have a better understanding, and also I will request you to practice it. Okay, so that will help you to like make that will help in making you understand it in from a practical and realistic point of view. Okay. So yeah, so let us carry on. So the load carrying capacity will be zero point 0.4 FCKAC plus 0.67 FYAS. Okay, so that is as per clause 39.3 P7 page 71 IS 456 2000. Okay, so yeah, so let us come to a problem. So in this problem, these are, say for example, these are the dimensions. Okay, 250 is the width of the column, 300 is the depth, and there are four rebars which are having 12 mm diameter. And yeah, and let us assume M20 and Fe415 grades of concrete and steel. Okay, so let us find the load carrying capacity of the column. Okay, so yeah, so how to do this? So basically area of concrete will be 250 into 300, right? So this is 75,000 millimeter square, and area of steel will be basically 4 into pi by 4 into 12 square, right? So it will be 452.38 millimeter square. So the percentage of steel will be 452.38 by 7. Like these are basic maths. So it will come around 0.603 percentage, right? So yeah, so the pu value. Okay, so as I told you, this is the standard equation. So pu equal to zero point 0.4 fck ac plus 0.67 fi as, right? So fck value is 20, fi value is 415, and putting the values we get 725 kilonewton. But here, as I just mentioned, and also raised by a student, so this value is not 100% correct. Okay, so because we have to subtract 75,000 with 452.38, because the FCK value is carried by only the area of concrete, but this is the gross area. Okay, so this is not actually the AC area, but this is just a representative example because it has been taught by sir. That's why also I am sticking with the same example. Okay, so but actually it will be subtracted by this, but as I told you, this value is very less as compared to this value, right? So even if you subtract this value, the value of pu will be somewhere near only about 724, 723. So there will not much of a difference. Okay, so that's why I think like the I think like sir has not tried to subtract. It is just for your explanation. Okay, but subtracting will be the actual case. Okay, so yeah, similarly, if we take the section as 250 and 250, so in this case area of steel will be the same. Okay, the 412 bars, so A's value will be 452 square, AC will be 62,500 square, right? So pu value in this case will be 625.678 kilonewton. Okay, so like if you see, uh, here it was 725 when we took how much 250 by 300, and here it is 625. Okay, so there is an abrupt change. Okay, when you reduce the section. Okay, so that's why the increasing the section increases the capacity, as you know, as expected, right? So in this case, the percentage definitely the percentage of steel will be higher because of the lower cross sectional area. Okay, so it is around 0.7232%. Okay, so yeah, so let us go to few more clauses for the reinforcement now. Okay, so if we go to page 48 of IS 456 2000, and if we follow clause 26.5.3 for columns, so here the main minimum reinforcement, okay, so it should not be less than 0.8%. Okay, so as per this is not a correct correct design. Okay, so we have to increase the number. Okay, even this is not a correct design. Okay, so it should always be greater than 0.8%. Okay, and it should not be uh, greater than 6%. Like it should be between 0.8 and 6%. It should be greater than 0.8 but less than 6. Okay, so that is the minimum reinforcement, and basically it is the longitudinal reinforcement. Okay, so that is the case of the for the cross sectional area of the column. We have to take reinforcement which is between 0.8% to 6% of the cross sectional area. Okay, and in case of rectangular column, the minimum number of bars should be 4, whereas in case of circular column, the minimum number should be 6. Okay, so these are the points we have to take into account, and bars should not be less than 12 diameter. Okay, so here, yeah, so here it was taken as 12, so from that respect the size is okay. Okay, so it should be between 0.8% and 6% area, okay, of the cross section. For minimum number of bars for rectangular column, it should be 4. Minimum bars for circular column, it should be 6, and the size of bar should not be less than 12. Okay, it should be greater than 12 for the case of the longitudinal bars. Okay, and for the case of spacing, okay, the spacing of longitudinal bars measured along the periphery of the column shall not exceed 300 Okay, so it should be less, okay, lesser than 300 okay, as per the requirements of the bars, number of bars, and this one, the number of bars, the periphery, and the this one, this condition should be maintained. Okay, it should not be exceeding 300 so that is for the longitudinal bars. Okay, now let us see the cases for lateral ties. Okay, so lateral ties basically that has to be provided based on these conditions. Okay, so pitch is basically nothing but spacing. Okay, so the spacing for lateral ties, it should be the minimum of these three conditions. Okay, one is the least lateral dimension of the compression member, second is 16 times the smallest diameter of the longitudinal reinforcement, and third is 300 millimeter. Okay, so the spacing of the tie bar should be given as such that it should be the minimum of the least lateral dimension of the section, the 16 times the value of the smallest diameter of the longitudinal reinforcement, and 300 millimeter. So out of these three, what is the lowest value? That should be the pitch. Okay, so the spacing of the lateral ties, and the size of the ties. Okay, so that should not be less than 1/4 of the diameter of the largest longitudinal bar. Okay, say for example in this case it should not be less than 12 okay, the longitudinal bars. So if 12 bars are used, then the lateral ties should not be less than 1/4 of 12. Okay, so that should not be less than 3 Okay, but as you know, 3 there is no rebars having size of 3 so definitely we'll be using at least 6 Okay, so that's the condition we have to make a use for the case of lateral ties. Okay, So yeah, so let us see a problem, a representative problem again. So if, let us assume that we need a column having a load carrying capacity of 1200 kilonewton, okay, and the grade of concrete is M20, grade of steel is Fe415, and we have to design a column section, okay. So yeah, so how will we proceed? Let us see that. So let us assume that we will be using 1% steel, okay, 1% steel, that is the 1% area of gross area, okay. So as will be 0.01 AC. This AC is actually AG, okay. So because it has been because as I told you, like the area of concrete is much higher than AS, so it is almost equal to AC, right? So this actually is AG, okay. So as we all know, the load carrying capacity will be estimated using this condition formula, which is PU equal to 0.4 FCK AC plus 0.67 FY AS, okay. So substituting the values, we will try to calculate the AC required, okay. So if you see here, the AC value comes out to be around 11312.09 millimeter square, right? So because nothing has been given as the nothing no no specifications of for the column has been given, so let us assume the size of the column is square, okay. So for like assuming it as square, we can just find out the square root and find the dimension, okay. So finding the square root of 11312.09, we get it as 333.63, okay. So required square column dimension will be 333.63 by 333.63 millimeter, right? So we have to provide a diameter, we have to provide a dimension which is greater than or equal to this value, okay. So let us make it an idealized one. So let us give a section of 350 by 350 millimeter, okay. So that section will have a gross area of around 122,500 millimeter square, okay. So which is greater than the required area, which was 11312.09 mm square, right? So it is okay. And the area of steel, we assumed it as 0.1% of this one, the gross area. So it will be coming about 1225 mm square, okay. So this based on this, the area of steel required, the longitudinal area, so we have to take longitudinal bars, right? So it should not be less than 12, okay. So if we consider 12 bars, so then the number of bars required will be 10.84, okay. And if we consider 16 bars, then the number of 16 bar dia bars, so the number required will be 6.09, right? So let us give the bars as 16 okay. So because it is 6, so let us give us 8. Actually we needed more than 6, that was actually we needed 7, okay. But to make it uniform, okay, so make it uniform, we are taking 8, okay. So it is equally distributed, okay. So let us provide 8 16 dia bars. So the dimension we have considered is 350 by 350 right? So the area of steel which will provide is 8 into pi by 4 into 16 square, which is 1608, okay. We needed 1225 and we have given 1608, so it is okay. So the percentage of steel is how much? It is coming as 1.31%, which is greater than 0.8%. As we discussed in few slides back, so amount of reinforcement should be greater than 0.8% and less than 6%, right? So we are finding as the p value as 1.31%, so which is greater than 0.8, so it is okay. And let us now design let us design for the lateral ties, okay. So for that, as we just discussed, so the diameter should always be greater than one it should not be less than 1/4 the diameter of the longitudinal reinforcement. So it is 1 by 4 into 16, okay, that is 4 millimeter, okay. So as we like 4 millimeter, as it is not available, so let us give 6 okay. Let us give 6 diameter of mild steel, because that is just for a requirement, okay. So let us give it 6 diameter ms mild steel, and the reinforcement will basically be what? It will be the least dimension of minimum of least dimension of lateral section, which was which will be in this case 350 16 times the diameter of longitudinal bar, which is 16 so 16 into 16, that is 256 and third is I think 300 right? Yeah, so 300 so it should be minimum of 350, 256 and 300 millimeters, okay. So that means it should be 256 right? So let us provide the spacing as a ideal value at a round out value, which is 250, okay. So let us provide a lateral tie of 6 diameter at a center to center distance of 250, okay. So based on the design, so this is the cross section and diagram. Okay, so the sketch, okay, sketch of the our design. So we have found out 350, we have designed a section which is having a the it's a basically square section having a dimension of 350 by 350 mm, and M20 is the concrete grade, Fe415 is the steel grade. The main reinforcements are 8 16 mm dia bars, okay, and tie bars are this one, okay. So it is having 6 mm diameter, and it is, you know, the spacing is basically, that is the pitch, okay. So that is basically 250 millimeter center to center. Now as I told you, here we could have given 7, okay, but to make it uniform we are giving 8 mm bars, okay, because it was around 6.08, that means we only needed 7, but to make it uniform we are giving 8, okay. So yeah, so let us see one more problem, okay. So design an axial loaded tied column pin at both ends with an unsupported length of 3.5 meter for carrying a characteristic load of 1500 kilonewton, okay. The concrete grade is M20, the steel grade is Fe415, okay. So this is one more problem. So we need to design an axially loaded, that is axial compressive load is acting on a tight column, okay, which is pinned, okay. So the we have to find the effective length based on the pin condition, pin at both ends, okay. That is having an unsupported length of 3.5 meter for carrying a characteristic load of 1500 kilonewton, right? And the concrete grade is M20 and steel grade is Fe415, right? So yeah, so as we just discussed, so we need to find the basically if you see na, so the design load is basically the factored load itself, okay. So that's why in most of the cases they consider the design as the factored load, okay. But there are some cases which consider, you know, which further multiplies the design with 1.5, okay. So it's better, it's better to see problems and to, you know, make sure what which will be the base condition. I feel like, you know, if the design load is given, so you can directly work with the problem, okay. So the pu value, that is a factored load value, will be 1.5 times the characteristic load, okay. So it will be 1.5 into 1500, okay. So that will be around 2250 kilonewton, okay. And the effective length for the pin condition, right? So it is pin at both ends. So for that case it will be, if you remember, it will be equal to the unsupported length, okay. So it is 1L if you remember. So L is 3.5, okay. So 1L will be again 3.5. So effective length L is 3.5 meter, okay. So yeah, so the LE by D value, okay, so LE by D value, we are assuming it to be a short column, okay. So assuming this to be a short column, so the LE by D value should be equal to 12, okay. So basically we always go for a short column, okay. So the columns which are present in houses, basically always they are the short columns, okay. So LE by D value, for that to achieve, it is 12, okay. It should be less than 12 or less than equal to 12. So in that case the D value, okay, so that should be LE by 12 or 3500 by 12, which is 291.666 mm, right? So assuming the section to be a square one, okay, so and rounding it off to a nearest nearest multiple of 10. So let us assume the size of column to be 300 by 300 mm, okay. So the size of column will come to be 300 by 300 mm, and let us see the minimum eccentricity, okay. So it should always be less than 20 mm as per the IS code. So that is calculated using this formula, L by 500 plus D by 30. So L is 3500, right, and D is how much? 300, right. So 3500 by 500 plus 300 by 30 is 17, okay. So 17 millimeter, and it is less than 20 mm, okay. So it is satisfied, okay. Also the slenderness ratio, okay, so that also that should be less than, we assume this value, okay, but it should always be the actual value should also be the lesser one, because for this condition the D was 291.6, right, but we assume the D value to be 300, so we have to again check, okay. So 3500 by 300 is 11.66, so it is less than 12. That means our slenderness ratio is also okay, okay. So now we have to compute the area of steel. So Pu value will be 0.4 FCK AC plus 0.67 FYAS, right? So Pu value is design load, AC concrete, AS steel area, FCK characteristic concrete strength, and FY is steel yield strength, right? So putting all these values. So if you see in this case, we have subtracted, okay? So we have subtracted the AC minus AS, okay? So that this is the ideal case. Ideally, this is how the equation should be solved, okay? So Substituting the values, we will see here that A's value is equal to 5665.61 millimeter square, right? And the percentage of steel P, that will come at about 6.29%, which we just discussed is greater than 6%, right? So we have to redesign, okay? And we'll be redesigning, but let us see a few more things here. So the area of steel is how much? 5665 mm square and 25 mm diameter bar. So A's bar will be it will be, for one bar it will be 491 mm square. So the number of bars required will be how much? 5665 by 491, that is 11.53. So in that case we have to provide 12 mm 25 mm 12 25 mm dia bar. So it will come like this, okay? And in this case the clear cover, assuming it to be 40 mm, so it will be how much? So the center to center distance, it will come to be uh, end to end distance of the bars, it will come to be 300 minus 40, that is 220 mm. And the center to center of the end bars, it will come to be 220 minus 25 by 2 minus 25 by 2, which is 195 mm, okay? So these are some of the measurements which are calculating, but we have to redesign, okay? So so that is what it is shown here. So the center to center of outer bars is 195 mm, and the distance between two center to center distance between two consecutive bars, it will be, because there are three center to center distances, so it will be 195 by 3, that is 65 mm, okay, in these distances. And the clear gap between two bars, okay, so that is n to n distance. So this will be again 65 minus 25 by 2 minus 25 by 2, that is 40 mm, okay? So these are some of the measurements which were intended to be, to show, which were intended to make you understand, okay, which were shown to make you understand how the design is made, okay? So in this case the P value will be how much? It will be 12 into 491, that is 12 into 25 mm dia bar area into 100 by 300 by 300, which is 6.54, which we calculated, okay? So we took it more, okay? So yeah, so it is anyways greater than 6%. And if say for example we have to lap, okay, so lapping is basically joining two bars end to end, okay? So if the reinforcement bar is ended somewhere in the section, but the column is not ended, so we have to again, we have to add one more bar and you have to fix this, right? So fixing is the, connecting two bars end to end is called lapping, okay? But all the bars are not connected at the same junction, okay? If that is done, then the section will be weak at that point, okay? So we always go for staggered lapping, that is we only join 50% of the bars, okay, at one section, and the 50% of the other bar other remaining bars will be joined at the some prior or later section, okay? So even if we do that, okay, so then the lapping is also done, then the P value is will increase by 1.5 times, right? So it was 12 in this case, so it will become 18. 1.5 into 12, so it will become 18. So it becomes 18 into 491 into 100 by 300 into 300, so that will become 9.82, okay? So already it was 6.54, which was greater than 6. Now multiplying by 1.5, it has become in 9.82, so which is not desirable, okay? So which is not less than 6%, so definitely redesign will be required, right? So to achieve this, what we'll do is, we assumed that we designed it initially for how much? I think it was 350, right? uh, uh, sorry, it was 300, right? So initially it was 300, so now let us go for 375, okay? So assuming the column section is 375 by 375 mm, so in this case again the E minimum value will be 3500 by 500 plus 375 by 30, that will be 19.5, so that is less than again 20 millimeters, right? And using this equation we try to find the AS value, which comes to be 4165 mm square, right? So the P value in this case is how much? 2.96%, okay? And even if you add the lapping thing, so it will be 1.5 into 2.96, okay? So it will be around how much? Between 3 to 4, like between 4.5 or something, like, yeah, around 4.5, right? So in any case that is less than 6%, so the design is okay, right? So here I think they have not added the lapping part, so only going for the reinforcement, they have found that the P value is 2.96%. So using 25 mm dia bars, the number of bars will be 4165, right, which is the area that is required, divided by 491, right? So that comes to be 8.48, okay? So we need 9 number of bars, but to make it uniform, let us provide 10 number of bars having 25 mm diameter. Okay, so the area of steel that will be provided will become 10 into 491 into 100, okay, divided by 375 into 375, which becomes 3.49%. So it increased from 2.96 to 3.49%, but in any case it is less than 6%, so the section is okay, right? So that is the design of the main longitudinal bars. Now let us go for the tie bars. So as we discussed, the tie bar should not be less than the size of the tie bar should not be less than 20, 1/4 of 25, the diameter. So it is 6.25, right? So we have to provide 7, at least 7. So definitely there is no 7, so let us provide 8 dia rebars for tie. Okay, and spacing will be minimum of dimension of column, which is 375, 16 times the diameter of rebar, longitudinal, which is 16 into 25, that is 400, and 300 right? So minimum of 375, 400 and 300, which becomes 300 only, right? So let us provide 85 lateral ties at 300 millimeter center to center. Okay, so that is how the calculation needs to be done. Okay, so that is how we have been designing for the columns having load and moments. Okay, so now if you see what is a what is a like the conditions. Okay, so if the mu value is 0, that is no moment, so it will be axially loaded condition, right? And similarly, if there is pu value to be 0, then it will be only moment, that is pure bending. Okay, and if both are present, so then both pu and mu are present. Okay, so how it is affecting, right? So if both are present, then as we discussed in the assumptions only, the maximum compressive strain at the highly compressed extreme fiber, which is epsilon c. Okay, so in if you see this diagram, okay, so say for example this is the section. Okay, this is the section. Okay, so this is the length of the section. Okay, so this part is having the maximum compression, that is the fiber with the maximum compression, and this side is the fiber with the maximum least compression or maximum tension. Okay, so in case of if you have gone to the beam case. Okay, so beam case, what happened, there was no axial load. Okay, only moment. Okay, so like this case. Okay, in beam case it was this case, pure bending. Okay, so in that case the strain diagram followed like this. Okay, so it started from 0. This is a compressive strain. Okay, strain, this is basically compressive strain. Okay, so this value started from 0 and it increased and ultimately it reached 0.0035, which we discussed in case of beam. Okay, but in case of column, okay, in case of column, this is basically the case, both pu and mu are present. Okay, in that case here it will not be 0. Okay, here it will be, there will be value of wc prime. Okay, so this is basically nothing but strain at the least compressed fiber, right? So in this case what happens is, here at the most highly compressed extreme fibers case, so the maximum compressive strain will not be 0.0035, right? It will be less. How much it will be? It will be 0.0035 minus 3/4 or 0.75 the this value, that is strain at the least compressed fiber. Okay, so that was what we assumed. Okay, like that is as per the assumptions. Okay, so this is a diagram which is validating that assumption. So the strain diagram will be something like that. Okay, so with the increase in fiber having compressive compression strain, the strain diagram will increase compressive strain. And in case of the outermost maximum compressed fiber, okay, so in case of beam it will be 0.0035, but in case of column it will be 0.0035 minus 3/4 of strain at the least compressed fiber. Okay, that is wc prime. Okay, but here it will never be 0 because it will be there will be some compressive strain developing. Okay, so yeah, so based on this and the pm interaction curves. Okay, so based on pm interaction curves, so this is the pm interaction curve. Okay, so based on this we have to find these ratios. Okay, pu by fck bd and mu by fck bd square. So if you see in this case, if based on plotting after plotting, if the value, if our point is somewhere here, okay, so that means mu component is 0. That means the column is axially loaded. Okay, because only pu value is there. Okay, if here, if the value, if the value which we get is here, somewhere here. Okay, so that means the pu value is 0, so that means it is no axial load, only flexure is there. Okay, if if point is somewhere here, it is the balance condition. That is, it is between, it is not a compression as well as tension, it is a balance condition. If it is higher than this and towards the pu by fck bd side, so it is the compression zone. And if it is in this side, below the balance condition, it is in the tension zone. Okay, so we will understand this when we solve problems in later classes. Okay, so this is the start of the column design. So as we go, okay, so we will understand how we will use this in solving problems. Okay, and these values are basically found from the for detailed explanation, you can refer to design aids of reinforced concrete IS 456 1978. Okay, so there it has been mentioned in detail. And this, okay, this has been published as a separate book, and that book is SP16. Okay, so you have to refer this SP16 for solving of this type of problems, where they have this given these values. Okay, for different this this curve. Okay, this curve is for a given d prime by d value. Okay, so this is a curve given by d prime by d value. So d prime is basically the distance from the topmost fiber to the center of uh, the rebar. Okay, from the top side, because from the bottom side it is the effective depth, right? From the top side, if you see, that is a clear cover plus half of diameter from the top side. Okay, so that is the d prime value. So we will solve this in coming classes. Okay, so that is for giving you a very very initial idea of how it is done. Okay, so that is how we will be using. So this is, you can refer to this code IS 456 1978. So this is basically the earlier version, and this study has also been published in SP16. Okay, so you can also refer this. Okay, mainly it is referred, we referred this only while solving. Okay, so yeah, so with this we will come to the close of the lecture part for this week's class. So now let us go to the solve problems. Okay, so yeah, so first question, a pedestal having cross-sectional dimension of 250 mm by 500 mm, its effective length is, as per IS 456, would be how much? A 1200 mm, B 700 mm, C 920 mm, or D none. Okay, so what will be the this one effective length for this pedestal? Okay, having a cross-sectional dimension of 250 mm by 500 mm as per the IS 456 2000 code. Okay, so if you go to the code, okay, as per clause 26.5.3.1, okay, the effective length of a pedestal should not exceed 3 times its least lateral dimension. Okay, we also discussed this in the initial slides of this class, right? So it should not exceed 3 times its least lateral dimension. Okay, so what is the least lateral dimension? It is 250 mm, right? So it is the least lateral dimension, so the effective length should not increase, should not be more than 3 times the least lateral dimension, or 3 times 250 mm, that is 750 mm. Okay, so which is this one, which is a value having the value less than 750 mm. So this is the value 700 mm, right? So its effective length will definitely be 700 mm, because it is less than 750 mm, right? So that's why 700 mm would be the correct answer. So what is the correct answer? It is 700 mm, or B. Okay, so B is the correct choice. Second question, for a rectangular column section, following nomenclature is followed. Okay, L is the effective length with respect to major axis of the section. Small l is the effective length with respect to minor axis of the section. Capital D, it is the overall depth of the section with respect to major axis, and small d is the breadth of the section. Okay, so if these are the nomenclature of the column length and sections, so in that case a column will be said to be a short column when a L by capital D and small l by small d both are less than 12. B, capital L by capital D and small l by small d both are less than 15. C, capital L by capital D and small l by small d both are greater than 15. D, capital L by capital D and small l by small d both are greater than 12. Okay, so what will be the case if a column is said to be a short column? Okay, so as we have studied, okay, and also as per clause 25.1.2, okay, a column has to be is called a short column. Okay, as per IS 456 clause 25.1.2, a column is said to be a short column if the slenderness ratio, okay, that is the L by dimension, depth or breadth, so slenderness ratio with respect to both axes should be less than 12. Okay, so in that case the column is said to be a short column. We also discussed this. So that means capital L by capital D as well as small l by small d, right? In both the cases the value should be less than 12. Okay, So that means A. Okay, so A is the correct option. So yeah, so as you can see, A is the correct option. That is L by capital D and small l by small d, both are less than 12. Okay. Third question, if both ends of a column are pin supported and its overall length is L, capital L, then which one of the following statements could be correct? A. Effective length of the column is 0.7 L. B. Effective length of the column is 1.0 L. C. Effective length of the column is 1.2 L. Or D. Effective length of the column is 1.5 L. Okay. So which one will be the out of this, which one will be the correct? Okay, if the column has an overall length or unsupported length of capital L and it is pin supported at both ends. Okay, so as I discussed with you in the initial classes, so if sorry, in the initial slides, so if it is pinned at both the ends, then the effective length is always equal to the unsupported length, right? So it is 1L, right? So it will be definitely equal to L only, or 1L, right? So B is the correct option. So as you can see, B is the correct option. Fourth question, as per IS 456-2000, maximum compressive strain in concrete subjected axial compression is to be considered as A 0.002, B 0.0035 minus 0.75 times strain at the least compression extreme compressed extreme fiber, C 0.0035, or D 0.002 minus 0.75 times at the least compressed extreme fiber. So if you see, maximum compressive strain at in concrete subjected to axial compression, right? So because it is maximum compressive strain in concrete subjected to axial compression. Okay, so that means it has to be 0.002 as per the IS code. But if both axial compression as well as flexure is there, okay, in that case it will be 0.0035 minus 0.75 times strain at the least compressed extreme fiber. Okay, so because it is only under axial compression, then we take the maximum compressive strain as 0.002. That is as per IS 456 clause. Okay, so this clause is 38.1a. Okay, so as per the clause 38.1a of IS 456-2000, maximum compressive strain in concrete subjected to axial compression is to be considered as 0.002. Okay, if only axial compression is there. Okay, so hence the correct option is A. So as you can see, A, that is 0.002 is the correct option. Fifth question, if a short column having overall dimension of 300 mm by 500 mm and 16 mm diameter of longitudinal bars, the maximum spacing between two lateral ties could be provided how much? 500 mm, 300 mm, 256 mm, or none of the above. Okay, so if you remember, what are the conditions for providing maximum spacing between two lateral ties? So there are three conditions, and it should be the minimum of those three. One is the least lateral dimension, which is 300 mm. One is 16 times the diameter of the longitudinal bar, which is 16 mm, and the third is 300 mm. Okay, so it should be a minimum of 300 mm, 16 into 16 into 16, that is 256 mm, and 300 mm. Okay, so minimum of 300 mm, 256 mm, 300 mm, which comes to be 256 mm. So C is the correct option. Okay, so this is what has been written also, and that is as per clause 26.5.3.2 C1 of IS 456-2000. Okay, so the maximum pitch or spacing should be minimum of this tree, which is coming to be 256 mm, right? So the answer is C. So as you can see, C is the correct option, which is 256 mm. Sixth question, a perfectly axially loaded concrete column of gross dimension 400 mm by 400 mm is reinforced with 4 bars of 20 mm diameter. Determine the design axial load carrying capacity of the column. Consider M20 M25 grade concrete and Fe 415 grade steel. Okay, so A 1015.25 kilonewton, B 1256.25 kilonewton, C 1422.54 kilonewton, or D 1936.84 kilonewton. So what will be the design axial load carrying capacity of the column if it is having a gross dimension of 400 by 400 millimeter and 4 rebars longitudinal of 20 mm diameter? Okay, and grade is M25 for concrete and Fe415 for steel. Okay, so we'll be using that equation, that is this one, 0.4 FCKAC plus 0.67 FYASC, right? So design axial load carrying capacity of column is this, right? So here, if you check, the width of the column is B, which is 400 mm, and D is also same, that is a square column. So D is also 400 mm. Diameter of the rebar is 20 mm. So you can see 20 mm. Number of bars is 4. So total number of rebars is 4. Grade of concrete is M25. So M25. Grade of steel is Fe415. So Fe415. So that means M25 is FCK 25 megapascal. Fe415 means Fy is 415 megapascal. Okay. And 4 number of 20 mm dia bars. So area of steel is 4 into pi by 4 into 20 square, which is how much? 1256.64 millimeter square. Okay. And what will be the area of concrete? So as I told you, we have to here it has been deducted. Okay. So ideally it should be deducted. So it is gross area, which is 400 by 400 minus area of steel. Okay, which is 1256.64. So what is the area of concrete? It comes to be 158743.36 millimeter square. Okay. So putting all the values in the question, we will get PU value will be zero point 0.4 into 25 into 158743.36 plus 0.67 into 415 into 1256.64. Okay. So that is the that comes out to be 1936.84 kilonewton. So the design axial load carrying capacity, okay, of the column, it is 1936.84 kilonewton. So it falls with the D option, right? So it is similar to D option. So the D is the correct option, which is 1936.84 kilonewton. Okay. Seventh question. A perfectly axially loaded square column subjected to a design load of 1500 kilonewton. If the unsupported length of the column is 4 meter and both ends of the column are pin supported, what would be the dimension of the column appropriately nearest multiple of 5? Assume area of steel provided 1.2% of the gross area of the column section, and grade of concrete and steel are M30 and Fe415 respectively. So what is the this one, what would be the dimension? So we require the dimension. We need to find the dimension. Will it be 300 by 300 mm, 415 by 415 mm, 400 by 400 mm, or 315 by 315 mm? So what will be the dimension? So we are given a design load of 1500 kilonewton. Okay. Unsupported length of the column is 4 meter, and both ends are, of the column are pin supported. Okay. So that means effective length is equal to unsupported length, right? And yeah, so area of steel, we are asked to assume 1.2% of the gross area of column, and M30 and Fe415 are grades of concrete and steel respectively, right? So what is the dimension of the square column, right? So let us see it. Okay. So if you see, design load is basically 1500 kilonewton. Okay. So that's why, as you can see, design load can be taken as the factored load. Okay. So that is the case. Okay. So please take the factored load similar to design load, but if it is characteristic load, always multiply by 1.5. Okay. So design load or factored load is 1500 kilonewton. Length of the column is this one, 4 meter. Okay. Grade of concrete is M30. Grade of steel is Fe415, and area of steel provided is how much? 1.2% of gross area of the column section, right? So as per again clause 39.3, that is the this equation for finding the axial loaded column carrying capacity. So as per this, the PU value, as we know, is this 0.4 FCK AC plus 0.67 FY AC, right? So substituting all the values, okay, we get the AG value, that is the gross area of the section, is 98732.2776 millimeter square. And because it is a square value, square column, so we'll just find the square root for finding the dimension, which comes to be 314.22 millimeter, right? So yeah, so we have to find the dimension nearest multiple of 5. Okay. So nearest multiple of 5 will be how much? 314.22 will become, yeah, 315, right? So in any case, it should be more only. So 315. So 315 by 315 mm will be the correct option. So D is the correct option. So as you can see, D is the correct option, which is 315 mm by 315 millimeter. Eighth question. A perfectly axially loaded column of size 500 mm by 500 mm is subjected to an axial factored load of 4500 kilonewton. If the diameter of longitudinal bars provided is 25 mm and concrete and steel grades are M30 and Fe415 respectively, what would be total rebar numbers that need to be provided to withstand the load? Okay, so will it be 6, 8, 10 or 12? So we need to find the total rebar numbers that is required for withstanding a load of factored load of 4500 kilonewton for a perfectly axially loaded column, okay, which is having a size of 500 by 500 mm dimension of the section, and the longitudinal bars have a diameter of 25 mm, and M30 and Fe415 are the grades of concrete and steel respectively. Okay, so what would be the total rebar numbers that will be required to provide for withstanding the load, right? So we need to find the number of rebars that is required, right? So for that we'll basically need the area of steel, okay, in column, right? So the design load, okay, or the factored load, okay, so that is the 4500 kilonewton value, right? So grade of concrete that is taken is M30, and grade of steel which is required is Fe415. Okay, so area of longitudinal bar, rebar, it is pi by 4 into 25 square. This is one. Okay, one area of one 20 mm by dia bar is 490.87 mm square, and as per again the clause 39.3, this is the equation for finding the design axial load carrying capacity of an axially loaded column, right, without any this one flexure. Okay, so find, putting the values, we will get the value of ASC. Okay, so ASC is basically 5638.04 mm square. Okay, and area of one longitudinal bar is 490.87, right? So number of steel bars required will be 5638.04 divided by 490.87, which comes to be 11.5, or rounding it off, it becomes 12. Okay, so D, 12 is the correct option. So as you can see, D is the correct option, which is 12. Okay, ninth question: a concrete column having gross cross-sectional uh, this one dimension of 450 mm by 450 mm and unsupported length of 4 meter is subjected to an axial service load of 1200 kilonewton. So find out the maximum eccentricity of the applied load along both axes as per the IS 456 2000, okay, from the center of the cross section, so that the section will be under compression only and no moment effect need to be considered. Okay, so both are 15 mm, both are 18 mm, both are 25 mm, both are 20 mm. So we basically need to find the maximum eccentricity of the applied load. Okay, so it should be we need to find the maximum eccentricity of the applied load so that it should only be compression. That's the column section. There should be no moment effect. Okay, so we have to find the maximum eccentricity for this case. Okay, for the column having a dimension of 450 by 450 mm and unsupported length of 4 meter, okay, and axial service load of 1200 kilonewton. Okay, so as per IS 456 clause 25.4, the maximum eccentricity, okay, that is calculated, the value of that will be the minimum of the unsupported length, that is L by 500 plus D by 30 and 20 mm. Okay, so or L by 30, 500 plus B by 30 and 20 mm. So it should be, it will be minimum of both these values. Okay, so if you see here, the unsupported length is how much? It is 4 meter, right? So width of the column section, it is 450 mm, right? So it is a square column, so both are same basically. And as per the clause 25.4, so along x direction it will be minimum of 4 by 4000 by 500 plus your 450 by 30 and 20. So it comes to be minimum of 23 and 20, which is 20 mm itself. So along x direction, so maximum eccentricity will be minimum of this two, so it will be 20 mm. Okay, and because the dimensions are same, so 20 mm will be the case for both the directions. So the maximum eccentricity that is allowed, so that the section is the section is only under compression, so the value will be 20 mm. So if you see, both are 20 mm will be the right options, that is D is the correct option. So as you can see, D, both are 20 mm is the correct option. Okay, and 10th question: in case of short columns, which of the following statements are incorrect? Okay, 1, area of longitudinal reinforcement shall not be less than 0.8% of cross sectional area. B2, diameter of longitudinal reinforcement shall not be less than 12 millimeter. 3, in case of rectangular column, minimum number of longitudinal reinforcement shall not be less than 4. 4, area of longitudinal reinforcement shall not be more than 8% of gross cross-sectional area. So which of the following statements are incorrect? A, 1 only, B, 2 only, C, 3 only, D, 4 only. So if you remember the conditions, okay, for the longitudinal reinforcements, so area of longitudinal reinforcement shall not be less than 0.8% of cross sectional area. That is true. Okay, it should be between 0.8 and 6%, right? So this condition is true. Second question, diameter of longitudinal second statement, diameter of longitudinal reinforcement shall not be less than 12 mm. So that is also right. Okay, so longitudinal reinforcement should start from 12 mm, not less than that. Third case, in case of rectangular column, minimum number of longitudinal reinforcement shall not be less than 4, that is also right. In case of rectangular column, the longitudinal reinforcement minimum number is 4, and for circular it is 6, right? So because in rectangular it is 4 and it is also mentioned here, so it is correct. Okay, so 3 is also correct. But if you see in the fourth case, the area of longitudinal reinforcement, it should not be more than 6%, not 8%. Okay, so it should be between 0.8% and 6%, not 8%, as we discussed in the initial slides also. So this is a wrong statement. Okay, so fourth is the wrong, incorrect. Okay, so D4 only will be the correct option. Okay, so as you can see also, you can refer clause 26.5.3.1 or also the initial slide. Okay, so statement 1, 2 and 3 are correct as we just discussed, and 4 is the incorrect statement. Okay, so yeah, so as you can see, D4 only uh, is the incorrect statement, and that's why it is the correct option. Okay, so D4 only will be the correct option, right? So yeah, so with this we come to the end of today's discussion. Okay, so let us again meet next Sunday and carry forward our discussion on columns. And yeah, so happy learning in the coming week. So with this I would like to end today's discussion. Thank you. Yeah.